Vessel calcification risk study using TDA geometry of 4 key inputs: PP, MAP, FPG, and VF. Number 1422, TDA Sharp 027, November 5, 2025. Gerald C. EclaireMD Foundation. Category: Vascular calcification, CVD, and stroke. Preface: as a 79-year-old male who has lived with type 2 diabetes since 1990, and experienced 5 cardiac events between 1994 and 2004, I have now fully stabilized both my metabolic and cardiovascular conditions since 2014. However, what about the vascular damages that had already occurred before 2010? On June 21, 2025, I suffered a hemorrhagic stroke near the pons area of my brain. A CT scan revealed extensive cerebral microvessel calcifications, with numerous bright white regions. My stroke doctors attributed this to chronic hypertension. However, based on my long-term data, I have never had chronic hypertension but rather transient episodes of acute high blood pressure under stress. This led me to investigate a deeper cause: the cumulative vascular damage built up from my earlier decades of poorly controlled diabetes and obesity. To complement my Viscoplastic Medicine Theory, VMT, analysis, I applied Topological Data Analysis, TDA, to study the same dataset through a geometric perspective. TDA focuses on the spatial shape, area or volume, and data connectivity of multidimensional health dataset. Instead of energy accumulation in my VMT analysis, it measures how biomarker interactions evolve geometrically over time, revealing contraction or expansion of health domains that reflect underlying biological stability or stress. Introduction. Over the past 16 years, I have self-studied medicine, and continuously refined my mathematical physical modeling approach through both VMT and TDA. While the VMT model quantifies energy flow and irreversible deformation of biological systems, the TDA model captures the shape of those processes in geometric space. Both aim to describe the same biomedical reality from 2 independent dimensions: physics and geometry. This paper, number 1422, serves as a direct geometric continuation of my previous VMT paper, number 1421, using the same dataset of 4 key biomarkers: pulse pressure, PP, mean arterial pressure, MAP, fasting plasma glucose, FPG, and visceral fat percentage, VF%. This TDA analysis explores how the topological geometry of these variables evolved from 2010 to 2025. The objective is to verify whether the geometric contraction pattern aligns with the 60:40 metabolic to hemodynamic ratio, previously derived from VMT energy analysis. Data preparation. The dataset spans 16 years, from 2010 to 2025. Covering annual averages of the 4 normalized variables, NVF, NFPG, NPP, and MAP. Each variable was normalized to its respective healthy reference. PP is 45 mm of mercury, MAP is 85 mm of mercury, FPG is 90 mg per deciliter, VF is 13%. The normalized values were then plotted in a 4D coordinate space, forming a topological manifold representing the state of vascular health for each year. The geometric relationships among these 4 axes, fading glucose, belly fat, pulse pressure, PP, and mean arterial flow, MAP, provide a multidimensional visualization of vascular stress and stability. TDA geometric model. In this analysis, I use 2 complementary geometric projections, 1.2D PCA, principal component analysis, to simplify the 4D manifold into orthogonal axes, PC1 and PC2, that capture the dominant and secondary variations among the 4 biomarkers. PC1 represents the major trajectory of vascular calcification health, combining overall metabolic load, FPG and VF%, with blood pressure, stability, PP and MAP. PC2 shows compensatory interactions between metabolic and hemodynamic factors, for example, when lower blood pressure balances higher glucose or fat stress. 2.3D Datapoint-Cloud and Datapoint's distance geometry to measure the overall volume, or spread of the 4-dimensional health space for each year. A large geometric spread indicates systemic instability, whereas geometric contraction reflects improved coordination and reduced physiological stress among variables, results in topological interpretation. In the finalized 3 TDA diagrams below, 1.2D scatter diagram, FPG versus MAP, clearly shows topological contraction from 2010 to 2025. 2.3D point cloud diagram, VF%, FPG, PP, displays multidimensional geometric contraction and stabilization. 3. Geometric contraction diagram quantifies the steady reduction in system volume over time, confirming progressive topological stabilization after 2018. From 2010 to 2012, the TDA geometric shape was large, irregular, and widely dispersed, consistent with a high-risk, unstable metabolic hemodynamic system. The calculated geometric distance among variables was maximal during this period, aligning with the highest VCRP values, 152-130. The shape was stretched primarily along the FPG axis, confirming that hyperglycemia was the dominant destabilizing factor. Between 2013 and 2018, the geometry contracted significantly. The PCA projection showed the manifold collapsing inward along both PC1, metabolic dimension, and PC2, hemodynamic dimension. This period corresponds to the rapid improvement phase under lifestyle management, mirroring the sharp VMT energy decline and partial system recovery. After 2018, the geometric shape stabilized into a compact, nearly spherical cluster with minimal year-to-year displacement. This steady-state topology indicates that the vascular system had reached its lowest stress equilibrium, a condition of structural stability but not full reversibility. The geometric shrinkage ratio between 2010 and 2025 was approximately 38%, closely paralleling the VMT energy dissipation trend that plateaued near 99% saturation. In topological terms, the manifold shape transitioned from an elongated hypercylinder, from 2010 to 2012, to a compact sphere, from 2018 to 2025. This geometric contraction represents the healing and stabilization of vascular function through improved metabolic control. However, because the topology never returned to a smaller, pre-disease baseline, it implies permanent vessel remodeling and partial loss of vascular elasticity. Discussion. The geometric findings of this TDA analysis are consistent with my earlier VMT energy model results. Both approaches, VMT and TDA, independently converge on the same biomedical interpretation. Vascular calcification is primarily driven by metabolic deterioration, while hemodynamic stress acts as a secondary amplifier. The PCA results revealed that FPG and VF% dominate PC1, contributing roughly 60% of total geometric variance, while PP and MAP load onto PC2, accounting for about 40%. This 60-40 ratio aligns precisely with the VMT energy ratio obtained from the same data. The geometric contraction seen after 2013 represents reduced variability and stronger intervariable coupling, a hallmark of system stabilization through lifestyle control. Moreover, the persistence of a residual geometric volume after 2018 reflects irreversible vessel stiffness, caused by calcified tissue and long-term metabolic damage accumulated before 2010. In other words, the topology of my vascular system improved, but could not fully revert to its youthful configuration, an example of geometric hysteresis, similar to the irreversible energy deformation observed in viscoplastic materials. Thus, both VMT and TDA confirm that vascular calcification behaves as a nonlinear, dynamic, and partially irreversible process. Energy reduction and geometric contraction describe the same physiological reality, through two complementary mathematical languages, physics and topology. Conclusion. This 16-year longitudinal TDA study validates the same conclusion. Reached through VMT, vascular calcification is governed predominantly by metabolic stress, 60%, with hemodynamic reinforcement, 40%. The topological contraction of my 4D biomarker space demonstrates that systemic vascular health can stabilize through sustained lifestyle intervention, but cannot completely reverse pre-existing calcified damage. The TDA geometric approach complements the VMT energy framework by visualizing how biological systems evolve in shape, continuity, and connectivity. Together, these two independent methods, VMT and TDA, form a dual confirmation that vessel calcification is both an energetic and geometric phenomenon. Progressive, saturating, and partially irreversible. This geometric analysis also illustrates the power of self-collected longitudinal data in reconstructing personal health topology, offering a non-invasive, dynamic tool for future medical studies of chronic vascular disease. Disclaimer: I write this paper not for fame, but to share what I have learned so others can understand their health, prevent disease, and live longer, healthier lives. This content is for educational reference only, and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights belong to the author. Gerald C.